Welcome to the session. Today we are going to discuss Euler graphs and Hamiltonian graphs. So in the previous session we discussed on walks and their classification. Now we are going to discuss Euler graphs and Hamiltonian graphs. Now what is meant by a Euler graph? Any connected graph that is contain a Euler circuit is called a Euler graph. Any connected graph that contains Euler circuit is called a Euler graph. So now any graph which is consisting Euler circuit. See what is meant by a Euler circuit. So here we have to go through the Euler circuit. So Euler circuit is known as a Euler's cycle or Euler's tool. If there exists a circuit in the connected graph that contains all edges of the graph, then the circuit is called an Euler circuit. The circuit is called a Euler circuit. Circuit is nothing but a closed walk. So the closed walk will contain all the edges of the graph. Then we can say that the circuit is Euler circuit. Whatever the edges available in the original graph, so the circuit consists all the edges. Or if there exists a walk in the connected graph that starts and ends at the same vertex and visit every edge of the graph exactly once with or without repeating the vertices, then that walk is called a Euler circuit. Then the walk is called a Euler circuit. It is a closed walk in which all the edges should be covered, all the edges should traverse only once, and with or without repeating the vertices while traveling the edges, and it is going to be without repeating the vertices or repeating the vertices, then whatever the circuit we are going to get, that is nothing but a Euler circuit. Or a Euler trial that starts and ends with the same vertex is called an Euler circuit. A Euler trial is nothing but, it is an open walk in which the vertices may be allowed to repeat. So here a closed trial or a Euler trial, or else that what is a Euler trial which is consisting, a trial is consisting all the edges. So whenever that is a starting vertex and ending vertex will be the same, then that is also known as Euler circuit. Next, or I can say that a closed Euler trial is called a Euler circuit. A closed Euler trial is called a Euler circuit. Both are in the same man. Now, or else another way, a graph will contain an Euler circuit if and only if all the vertices of even degree. So whenever all the vertices, if you are going to consider, then the degrees we have to consider. If all the degrees are even, then we can say that the graph is the graph contain Euler circuit. Let us go for some of the examples. Now let us go for this. So this graph is Euler circuit does not exist here in this graph. Why? We are going to consider a path. Let us say a closed walk. Let us say I am going to consider A to B and B to C, then C to D, then I am going to move. Next, either I can move to B, then the same edge will traverse, repeat to cover this edge, so that we are not going to get any closed circuit, any closed walk. Suppose if I am going to move in any one direction, one edge has to be traversed more than once. So vertices are allowed to repeat, but edges are not allowed to repeat. So this is known as a Euler circuit, but it is not possible here. So Euler's circuit does not exist in this graph. And whereas we are going to consider, or else we are going to say that whatever a graph will contain Euler circuit if and only if all the vertices are of even degree. So I am saying that what is the vertex degree is 3 and this vertex degree is 3, which is not even. So Euler circuit is not possible from this. And the next another one is, if I am going to consider this, so here all the edges of degree even, this is 4 and this is 4 and the remaining all are 2, so which is even. So we can get an Euler circuit. Euler circuit. What is that Euler circuit? Let us go for A to B, one edge, and B to C I am going to move, and next C to D, and next from D to F, and F to B, and B to E, and E to D, and next D to A. Here the vertex D is repeated twice, whereas B is also repeated twice, but edges are not repeated. Edges are not repeated. So this is having a Euler circuit, and that Euler circuit is this. Now let us go for the other example. So here we are going to discuss this. Here Euler circuit does not exist because the degree of this is 1, whereas the degree of this is 1. So Euler circuit is not possible in any manner that we traverse from one vertex to another vertex. So it is not does not consist in Euler circuit. Now the thing is, a graph is said to be Euler's graph if it is containing the Euler's circuit. If it is containing Euler's circuit. Now, or whether the graph is containing Euler circuit or not, already we discussed by using this theorem. That means any connected graph is called a Euler graph. If and only if all the vertices of even degree. So whenever all the vertices are even degree, then we can say that the graph is Euler's graph. Or we can say that the graph is consisting a Euler circuit. Let us consider the example of this, and whether we have to find out whether the graph is a Euler's graph or not. For that, we are going to verify. See, all the degree vertices are even. Let us move like this. So here, all the vertices degrees are even. So there is a possibility. Definitely we can say that the graph is the Hamiltonian circuit. The graph is consisting Euler circuit. So here, what is that Euler circuit? Let us say that B to A, A to B to A, then what is that B to A, then B A to C, then C to E, then E to D, then once again it is C, then once again it is B. So here it is a beginning and ending vertex will be the same. So it is a closed walk in which all the edges, that means suppose let us say E1, E2, E3, E4, E5, E6 if I am taking, then it is E1, next E2, next C to E, E3, next E to D, E4, and D to C, E5, and C to B, E6. See, all the edges are covered which the graph is having. So we are saying that this is a Euler circuit. So subsequently we can say that the graph is a Euler's graph. Now, what is a Euler's trial or Euler's walk? A Euler's path is known as a Euler's trial. A Euler's path is known as a Euler trial, or we can call it as a Euler's walk. See here, if there exists a trial in the connected graph that contains all the edges, trial is nothing but an open walk. Which is vertices are allowed to repeat, in which edges will not be allowed to repeat. If edges are not covered, which edges are not covered of the original graph, then all the edges are not covered, then we are saying that simply it is a trial. If the trial is consists all the edges of the graph, then we can say that without repetition of the edges, then we can say that trial is Euler's trial. The trial is Euler's trial. So, or another way, if there exists a walk in the connected graph that visits every edge of the graph exactly once, every edge of the graph exactly once, with or without repeat, the vertices, then that walk is called a Euler's walk. Then the walk is called a Euler's walk. In so many ways we can discuss the Euler's walk or Euler's trial. So we already discussed. Now let us go for Euler's path or Euler's walk. So what is that? It should be a open walk and it should cover all the edges. It should cover all the edges. Let us go for the example. Now I am taking B to C and the next C to D. Then another one is D to B. Then we have to move B to A and next A to D. That means this is B and D. This is open. This is open walk. Let us, I am going to consider the edges are. So we are taking that E1, E2, E3, E4, E5. Let us, I am saying that. Then the open walk is, let us say, B, E1. So I am just taking B, E1, then E1, C, E2, D, E3, B, E4, and A, E5, D. So here, beginning and ending vertex are different and all edges, it has covered all the edges. So we can say that. This graph is having Euler's path and the path is this one. The path is this one. And similarly, this is also we are going to say that the Euler's path. Let us say B to C and C to D and next D to F and F to B and next F to B and next B to E and next E to D and next it is D to A and next and A to B. So it is a Euler's circuit. We are saying that it is a closed path will be there. Suppose whether the closed path is exist or not, that we have to consider. Let us go for this way. That means I am just moving, starting with this, and I am going to move like this, and I am going to cover like this. So I am going to get here a Euler's circuit. And if I am going to consider in another way, like this, and next, then see if I am going to take in this order, then I am going to get the Euler's path. Now this is Euler circuit. Now here it is not having any Euler's path does not exist. So let us go for A to C, C to D, and I cannot move. If I am moving that once again to cover these two edges, I have to traverse once again. So here Euler's path does not exist. Okay, in this way we are going to say what are the Euler's paths. Next Euler circuit we already discussed. Now this is it does not have a Euler circuit, so we can say that it is not a Euler's graph. And this is having a Euler circuit, so we can say that this is a Euler's graph. And next, this does not having a Euler circuit, so it is not a Euler's graph. So here some of the examples, just by observing the degrees of each and every vertex degree, you can say that whether it is a Euler graph or not. So here, the vertex degree, first example is 4, and this is a 2, and this is a 4, and this is 2, this is 2, this is 2. All vertices degrees are even, so we can say that this is a Euler's graph. So now here, the vertex degree is A is 1, B, C is 1, so which is not even. So vertex degrees are odd. Some of the vertex are 1 or 2. Any one vertex degree is odd. Then it is not Euler's graph. Then it is not Euler's graph. And then similarly, if I am considering third one, so here the vertex degree is 3, which is odd. So it is not Euler. It is not Euler's graph. And then here it is a 4 vertex degree, and here it is 3. So this is also not Euler's graph. And now this is a 2, 2, 4, 2, 2. So this is Euler's graph. Now, and here this vertex degree is 3. So it is not Euler's graph. It is not Euler's graph. So these are the simple way that we are going to verify whether the graph is Euler's graph or not. We just verify the degree of each and every vertex is even. Then we can say that it is having a Euler circuit. Subsequently, it is known as a Euler's graph. Otherwise, it is not. Now, what is applications of this Euler's graph? So one of the application is Coincible bridge problem. So Coincible is a former name of a city in Germany that is now in Russia. The following picture shows the inner city of Coincible with the river Pregel. The river Pregel divides the city into the 4 landmark areas. 4 landmark areas. The river is flowing like this. Landmark, this is A. This is next, the whole thing is B. The whole thing is C. And this is D. So it is going to divide. The river is divide the city into 4 land areas. Those land areas we are calling it as A, B, C, D. In order to travel from one part of the city to another part of the city, there are bridges will be there. So there are 7 bridges will be there. That is 1 bridge here, 2, 3, 4, 5, 6, 7. So from this landmark, if you are going to B to C, and we have to move to B to A and A to C. And suppose there is a person who is there in the land area C, then they have to come to D and then they have to come to B or anyway, any other part. They will come to C or they will come to D and they will come to B in any manner. They are having only 7 edges. Now, what is the Coincible bridge problem? Coincible bridge problem. Now, this is the question, that is it possible for anyone to cross each of the 7 edges only single time and come back to the beginning point without swimming across the river if we begin this process from any of the 4 land areas that are A, B, C and D. So here you select any one land area and you have to cross. You have to pass the bridge only once and you have to go to the another landmark, and from there you have to cross another bridge. So you have to cross the bridge only once and you have to return to the same point. Whether is it possible or not. Is it possible or not? So here for that we are going to construct this in the form of graph. After that we are giving a solution for that. So vertices represents land areas. So here there are 4 land areas are there. So land areas we are going to construct, it is the vertex. So land areas we are considering as vertices, and bridges we are considering it as edges. So while we are going to consider the land areas as vertices, means this is A and this is D, and the next another one is this is C, another landmark, and another landmark is B. So now A to D, there is one bridge is there. Then A to C is one bridge is there. A to C. And C to A will be there another. And next, if A to B will be there. And B to A will be there. And another one is C to D, another bridge is there. C to D is another bridge. And next, B to D is also another bridge will be there. So there are 7 bridges. See here, 1, 2, 3, 4, 5, 6, 7. So there are 7 bridges. Now starting from any one vertex, and you cross all the edges only once and reaching to the same vertex. That means either it is a Euler's circuit is possible or not. That means any circuit, any closed circuit means beginning vertex is equal to the ending vertex. So here, any circuit which is having all the edges of the graph, that means all the edges it crosses only once. All the edges it crosses only once and reaching to the same point, reaching to the same vertex. That means whether the graph is having Euler's circuit or not. So that is the question. So from this, the graph is having Euler's or not. So this is nothing but just we are going to verify the degree of the vertices. So here C degree is odd and B degree is odd, D is also odd. So any one is odd, then we can say that it is not possible. It is not possible to move from any one vertex to cover all the edges and reach into that particular vertex. So this is the another way of representation. So this is A to C and B. Just I am taking in this way. And we are going to connect whether the Hamiltonian, Euler's circuit is possible or not for that. So it is not possible because the degree of this is odd degree. So it is not possible for getting a Euler's circuit. So this is the related things which are necessary for the Euler's graph. Now, Hamiltonian graph. What is a Hamiltonian graph? So here, before knowing a Hamiltonian graph, what is a Hamiltonian circuit? Because the graph is said to be a Hamiltonian graph. So if it consists a Hamiltonian circuit, then we can say that the graph is a Hamiltonian graph. So what is a Hamiltonian circuit? A simple circuit G that passes through every vertex exactly once. Euler says every edge exactly once. So here every vertex should be exactly once. Their edges should be exactly once. So here vertex should be exactly once. So here a circuit which consists all the vertices are, it is passing through all the vertices of the given graph. If given graph, then that is known as a Hamiltonian graph, Hamiltonian circuit. Any circuit which is having all the vertices of the original graph, not only having all the vertices of original graph, but it appears only once, except the beginning and ending vertex. So that circuit is known as a Hamiltonian circuit. So unlike Euler's graph or Euler circuit, there is a simple, necessary and sufficient condition will be there to determine if there is in Euler's graph, we can say that the degree of each and every vertex degree is even. Then we can say that that graph is a Euler's graph and it is having a Euler circuit. So like that, there is no simple, necessary and sufficient condition to determine whether the graph is Hamiltonian graph or not. That means it is having a Hamiltonian circuit or not. So there is no specific rule. There is no necessary and sufficient condition to determine whenever we are given any graph, directly we can say that the graph is by using that concept, by using that condition, we can say that either whether it is a Hamiltonian graph or not. So there is no such provision here. If there is a vertex degree 1 in the graph, provided if there is a vertex of degree 1 in the graph, then it is impossible to have a Hamiltonian circuit. You have a Hamiltonian circuit. Any pendant vertex will be there. Any pendant vertex will be there. To reach that particular vertex, once again, we have to back to the same vertex. We have to traverse one vertex more than once. So it is not at all possible. And here, there are certain theorems which will give sufficient but not necessary condition for the existence of the Hamiltonian graph. So here, Hamiltonian walk in the graph is a walk that passes through each vertex exactly once. Each vertex exactly once. So that means it is a open walk. It is a open walk. Now let us go for the theorems. One is a Dirac theorem. So if G is a simple graph with n vertices, and n is greater than or equal to 3, and degree of V, if degree of every vertex, is greater than or equals to n by 2 for each and every vertex, then the graph is a Hamiltonian graph. And another one is a Force theorem. So Force theorem, if it is greater than or equals to 2 number of vertices, provided if it is a simple graph, then the degree of x and y. What about x and y are non-adjacent vertices? Non-adjacent vertices. If x and y are non-adjacent vertices, then the degree of x and the degree of y, that means the sum of the degrees is greater than or equal to n. Greater than or equal to n, which is the number of vertices. Then we can say that the graph is Hamiltonian. So this is true for some graphs and it is not true for all the things. So let us consider the graph of example is here, and I am going to consider any non-adjacent vertices. Let us say A and C. A and C are not non-adjacent, or B and D are non-adjacent, or next which is E vertices is adjacent to all. So now, and D, these are only the AC and DB are non-adjacent vertices. What is the degree of A? Degree of A is 4. And what is the degree of A is 3. Sorry, degree of A is 3. And the degree of C is also 3. What about the sum of the degrees? So 3 plus 3 is greater than or equal to how many vertices? So 6 is greater than or equal to 5. So you can say that the graph is a Hamiltonian graph. The graph is a Hamiltonian graph. So that means some of the graphs which satisfies this condition, then we can say that that is a Hamiltonian graph. Now similarly for the next also, we can consider this is having a pendant vertex. F vertex degree is 4. Then we can consider in the same way also vertex degree is 3 and vertex degree is 4. So now 4 I am going to get, and which is not greater than the number of vertices. So we can say that it is by Force theorem, the graph is not Hamiltonian. Or the graph is having a pendant vertex. So of degree 1 vertex. So we can say that it is not a Hamiltonian graph. Now, so go for the other example. If there is a graph with 6 nodes, now we have to determine whether the graph is a Hamiltonian graph or not. Hamiltonian graph or not. So for this, so we have to verify. See here, non-adjacent vertices. What we are going to take. This is what we are taking. This is let us say B and D, non-adjacent. So now these two are non-adjacent. So what is the Force theorem is G is a simple graph where degree of 1, degree of x plus degree of y for each pair of non-adjacent vertices. So if the condition is true, then we can say that it is Hamiltonian. But here, this is not true here. For every non-adjacent, it is not true. It is here 2, here to 4, and whereas non-adjacent is, then this is which is less than the number of vertices, which is less than the number of vertices. And we are going to verify whether it is a Hamiltonian graph or not. Hamiltonian graph or not. So, or else another way we can say that, so the degree vertex is 4 only. So, 4 is less than the 4, 5, 6. Number of vertices are 6. So, again we can say that this is not a Hamiltonian graph. Whereas the other way that we are going to verify just by moving from taking any one vertex and moving the corresponding vertices. So here if I start from any one vertex, C to B, B to A to E, F and F to D, then E, then I cannot move further to cross C. So I am just moving in any, let us say B to C if I am moving and C to D if I am moving. So these 3 vertices are over. Now I am going to this 4th vertex and then I am going to move this 5th vertex. Then I am going to move this 7th vertex. Then if I have to start from this, so either I can connect like this, then I can get a closed walk, but it does not cover the vertex E. Whenever E is covered, then I have to traverse once again back A and once again to B. That means vertex is repeated. So this is not a Hamiltonian graph. So now let us go for the other example. In the graph, it is having 7 nodes. Now we have to determine whether this is a graph of Hamiltonian or not. So now let us go for 7 vertices this is having. Now just to start from any one vertex to A to B and B to C and next C to D and next E and next F and G and next F and next A. Like this, if you are going to move this A to B and B to C, C to D, D to E, E to G, F, then A. It is not necessary to traverse all the edges. So it is a Hamiltonian cycle. Or else we can consider what are the non-adjacent vertices. Let us say B and F. So this is 6. So 6 is non-adjacent vertices are 6, B and F if you are going to consider. So the degrees are 6, but how many number of edges will be there? There are 7 number of vertices are there. 7 number of vertices are there. So 6 is, what is the Force Theorem? So what the Force Theorem is saying that, so degree of x, degree of y should be greater than or equal to, then we can say that a Hamiltonian graph. But here, even though it is not satisfied, then we can say that the graph is a Hamiltonian graph. And similarly, we can verify, just we are going to consider whether it is possible to get a closed loop. Then it is which covers all the vertices. Then we can say that it is a Hamiltonian graph. Let us say A to B, another example. And next this is E, and next F, next G, next H, next I, next D, next C, and next let us move to I am just moving B to D. I cannot move to A. Let us move another way. Then I am just moving A to B, B to C, C to D, and next D to E, E to F, F to G, G to H, H to I. From I to, like this, we are going to move to A. So A, B, C, D, E, F, G, H, I to A. So we can say that this is also a Hamiltonian graph. This is also a Hamiltonian graph, and the Hamiltonian circuit is like this: A to B, B to C, C to D, E, F, and next G, and H, and I, then A. This is a Hamiltonian circuit. Now here, in this following graph, let us say that, is it possible to get a Hamiltonian cycle, Hamiltonian circuit or not? So here, let us, I'm just moving. So here, let us say A to E, and E to B, then B to C, and then C to D, and next I am going to move to D to B. No, it is not possible. Then when in another way also, just A to B, then E, then it is not possible. We are not going to get any circuit without crossing, without vertices should not be repeated. It is not possible to cover from the beginning vertex to ending vertex. So this graph is not a Hamiltonian graph. And the next another one is determine whether there is the graph is contain Hamiltonian path or not. Hamiltonian path means any path which is having all the vertices of the graph. So let us say A, next B, C, and next another one is so we are going to move. Let us say that A to F2, we are just taking F to A and A to D, C and B. So it is not possible. Let us say all the vertices should have to cover all the vertices. F to A, next B, next C, next D. Once again I have to traverse. No, it's not possible that we are not going to get any Hamiltonian path from this graph. Hamiltonian path means it should be open. It should be open in which all vertices should be exist. And one more thing is, if I started from any one vertex, the remaining all vertices should be there in between 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. These vertices should be in the middle of the path. Then only we are saying it is a Hamiltonian path. So here Hamiltonian path does not exist. There is no specific rule that by using that condition we can say that this is a Hamiltonian circuit, like a Euler circuit. Euler circuit, we can say that each and every vertex degree is even. We can say that it is having a Euler circuit, but it is not possible in this. So what are the differences between these two? So Euler circuit traverses every edge, and here vertices, number of vertices repetition will not be considered. So here it is going to concentrate only on edges. Each and every edge should cover only once. And Hamiltonian circuit, any number of edges, so it is not necessary, may repeat the edges or may not cover the edges, but it should traverse vertices are only once. Hamiltonian circuit may repeat the edges. Then Euler's circuit may repeat the vertices, and Hamiltonian circuit visit each vertex exactly once. So path in Euler circuit is called Euler's path. Path in Hamiltonian circuit is called Hamiltonian path. So here these are the differences. So Euler's circuit traverses every edge exactly once. Hamiltonian circuit may repeat the edges. Euler's circuit may repeat the vertices. Hamiltonian circuit visit each vertex exactly once. Path in Euler's circuit is called Euler's path. Path in Hamiltonian circuit is called Hamiltonian path. So these are the differences, some differences between Euler circuit and Hamiltonian circuit. So with this, I am just concluding this. We will meet in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.